Welcome to the course on Machine Learning Foundations. I am Harish Ramaswamy, one of the instructors for this course. In the first week, we will look at the basic foundations, terminology, and introduction to machine learning, and set up key problems that will be referenced throughout the course. A natural starting question is, what is machine learning? You may have heard the term widely in news and media, but formally, machine learning is defined, for example, on Wikipedia as the study of computer algorithms that improve automatically through experience and data. This is a concise definition, but it raises further questions. What is an algorithm? What does improve automatically mean? And how exactly is data used? We will clarify these ideas throughout the course. Before going deeper, it is useful to recognize how common machine learning already is in everyday life. For example, weather prediction systems you use on your phone or search engines rely heavily on machine learning. While not the only tool used, it has significantly improved the accuracy of forecasts compared to decades ago. Another example is face detection in cameras. Modern smartphone cameras can detect faces in an image and adjust focus automatically, prioritizing people's faces rather than the background. This is also driven largely by machine learning systems trained on large amounts of image data. To understand machine learning, we introduce the idea of a task. A task is any process that converts an input into an output. Tasks can be performed at different levels. At the lowest level is manual labor, where humans directly process inputs to produce outputs. One level above that is tool usage, where humans create tools that perform the task instead of doing it manually. Programming is a special case of this, where the tool is software running on a computer. At a higher level is machine learning, where humans do not explicitly program the rules of the tool. Instead, they provide a general design framework and data, and the system learns how to construct the tool automatically. As we move up these levels, the abstraction increases, and the human's direct involvement in defining rules decreases. The question then becomes, why use machine learning at all, since programming seems simpler? The answer is that if a task can be solved effectively with manual labor or programming, those methods are preferred. Machine learning is used when those approaches fail due to scale, complexity, or the inability to explicitly define rules. In many cases, we do not know how to write explicit rules that map inputs to outputs, or doing so is impractical. However, machine learning also requires conditions to work, most importantly, the availability of sufficient data, and some underlying structure in the problem. To illustrate, consider a password verification task. This cannot be done manually at scale, but it is easily solved using programming because the rule is simple. Check whether the input matches stored data. Machine learning is unnecessary here. Now consider face detection. Humans can recognize faces easily, but it is very difficult to write explicit rules in code that define what a face is in terms of pixels. This makes programming impractical. However, machine learning works well here because we can provide many labeled examples of faces and non-faces, and the system learns the pattern. Next, consider weather prediction. Given radar data such as wind, moisture, and pressure, the task is to predict future weather conditions. Humans cannot easily derive the exact physical mapping from data to outcome in a usable way, and programming explicit rules is also infeasible. However, we know that such a function exists in nature, and we can collect large amounts of historical weather data. This makes it suitable for machine learning. From these examples, we can summarize: manual labor fails due to scale and inefficiency. Programming fails when rules are too complex or cannot be explicitly defined. Machine learning succeeds when we have data and an underlying pattern exists, even if we do not know the exact rules. Machine learning is already widely used in practice. One major application is email spam detection. Modern email systems classify incoming messages as spam or not spam automatically. This is difficult to implement with explicit rules because spam content is highly variable. Instead, Systems learn from large datasets of labeled spam and non-spam emails. Another major application is recommender systems, such as those used by Amazon, YouTube, and Netflix. These systems suggest products or videos based on user behavior and patterns from similar users. Explicitly coding human preferences is not feasible, but learning from large-scale behavior data is effective. Voice assistants like Alexa, Siri, and Google Assistant also rely heavily on machine learning. They convert speech into text and then into commands. This involves recognizing speech patterns and interpreting meaning, both of which are learned from data rather than explicitly programmed rules. Machine learning is also used in robotics, such as Mars rovers. These systems must make decisions in uncertain environments where pre-programmed rules are insufficient. In games, machine learning has enabled systems to surpass human performance in complex games like Go, which was previously considered too difficult for computers to master. Finally, machine learning plays a major role in industry applications such as digital advertising, where systems decide which users should see which ads to maximize effectiveness under budget constraints. Overall, machine learning is used when problems are too complex for manual solutions or explicit programming, but where sufficient data exists to learn effective patterns. In the next section, we will go deeper into how machine learning systems actually work. Here's a cleaned, listenable version of the lecture text. Machine learning is built on three core ideas: data, models, and learning algorithms. Data, in machine learning, usually means a collection of vectors. Each example in a dataset is represented as a list of numbers. For instance, a house can be encoded as a vector containing features like number of rooms, area, distance to metro, and price. On its own, this is just numerical structure. Its meaning comes from metadata, which explains what each number represents. Without metadata, data is just consistent numerical patterns that a computer can process. A model is a simplified mathematical representation of reality. It captures patterns in data without perfectly matching reality itself. Examples outside machine learning include physics laws like Newton's gravity equation or the ideal gas law. These are not exact, but they are useful because they approximate reality well enough to make predictions and decisions. In machine learning, models are mainly of two types: predictive and probabilistic. Predictive models are used to forecast outputs from inputs. Within this category, regression models predict continuous values, like house prices based on features such as size and location. Classification models predict discrete categories, such as whether a house is close or far from a metro station. Probabilistic models are different. Instead of predicting a single outcome, they estimate how likely different outcomes are. For example, they can estimate how likely it is that a randomly chosen person lives at a given location, or how likely a tweet was generated by a particular user. These models assign scores to possible configurations of reality. A learning algorithm is what connects data to models. It takes a collection of data and produces a model by selecting the best parameters from a family of possible models. For example, in a house price model, the structure might be fixed as a linear equation involving area, number of rooms, and distance to metro. The learning algorithm's job is to determine the best values of the coefficients using data. In this framework, the model is the tool that transforms input into output. The learning algorithm is what constructs this tool from data. The human does not explicitly write the final model, but defines the structure and allows the algorithm to learn from examples. Machine learning systems therefore consist of data as input, learning algorithms that process this data, and models that perform predictions or probabilistic scoring. The next step is to study how these systems are trained in supervised and unsupervised learning settings. This lecture explains supervised learning in machine learning, especially regression. Supervised learning means you are given training examples. Each example has an input and a correct output. The goal is to learn a rule that takes inputs and produces outputs that are as close as possible to the correct ones. First, we define some basic terms. A real number means any normal number like 2.3 minus 7.6 or the square root of pi. A vector is just a list of real numbers. For example, a three-dimensional vector could be 3.6, 5.2, and minus 1.8. We often work with collections of vectors. Each data point is one vector. Each vector has multiple components. To refer to parts of a vector, we say things like the first coordinate or the second coordinate. We also use something called an indicator function. This simply means if a condition is true, the output is 1. If it is false, the output is 0. For example, 2 is even, gives 1, and 2 is odd, gives 0. Now we move to supervised learning. Supervised learning can be thought of as curve fitting. You are given many points. Each point has an input and an output. Your job is to draw or learn a curve that best fits all those points. Each input is a vector, and each output is a label. The label could be a real number like price, or a category like yes or no. The goal is to find a function that takes an input vector and predicts the correct output label. We want the predicted output to be as close as possible to the true output for all training examples. To measure how good a model is, we use something called a loss function. The loss function measures the difference between the predicted value and the actual value. A common idea is take the difference between prediction and actual value, then square it, then average this over all data points. If the loss is 0, it means the model is perfect on the training data. Now we talk about regression. Regression is a supervised learning task where the output is a real number. For example, predicting house prices. A simple regression model assumes the output is a weighted combination of the inputs. For example, the price of a house might depend on number of rooms, size of the house, and distance to the nearest metro station. Each of these inputs is multiplied by a weight, and then all are added together with an extra constant term, so the model learns how important each feature is. Now classification. Classification is similar, but instead of predicting a number, we predict a category. For example, we might predict whether a house is close to the metro or far from the metro, so the output is not a continuous number. It is a label like close or far. A classification model uses input features and produces a decision rule that assigns one of the categories. Now we talk about learning algorithms. A learning algorithm is the method that takes data and produces a model. Before seeing data, we choose a type of model, like linear models. Then the algorithm looks at the training data and adjusts the parameters of the model to fit the data as well as possible. These parameters are numbers inside the model that control its behavior. For example, in a house price model, the algorithm learns how much weight to give to number of rooms, how much weight to give to distance, and so on. To understand this, imagine a simple example. Suppose we have several data points where the input is just one number and the output is another number. We tried two possible models. The first model multiplies the input by 2. The second model takes the input, adds 3, and uses that as the prediction. We compare both models by checking how close their predictions are to the actual values. We compute the average square difference between predicted and actual values. The model with the smaller error is considered better, so the learning algorithm chooses the model that best fits the data. In real machine learning, the algorithm does not just compare two models. It searches through a large space of possible models and finds the one that minimizes error. Finally, the key idea is this: machine learning is about learning a function from data using a rule that minimizes prediction error, so that the learned function can generalize to new unseen examples.
Hello everyone, and welcome to another lecture on machine learning foundations. In this lecture, we continue with supervised learning and focus on the classification problem, along with some concrete examples. A simple classification task looks like this. You're given input such as a house's area and price, and you want to predict whether the number of rooms is greater than 3 or less than or equal to 3. This is classification because the output has only 2 possible categories. In supervised learning, the training data consists of pairs of inputs and outputs. Each input is a vector in a real-valued space, meaning it is a list of numbers. Each output in classification is not a real number, but instead belongs to one of 2 labels, typically +1 or -1. So unlike regression, where outputs are continuous numbers, classification outputs are discrete categories. The learning algorithm produces a model, which is a function that takes an input vector and outputs either +1 or -1. To evaluate how good a model is, we use a simple idea. We measure how many training examples are classified incorrectly. We compute the fraction of mistakes the model makes on the dataset. This is called the classification loss. To make predictions, one common model is a linear separator. This works by first computing a weighted sum of the input features, adding a bias term, and then applying a sign rule. If the result is positive, the output is +1. If it is negative, the output is -1. So the model works like this. Multiply each input feature by a weight, add everything together, add a bias, and then decide the class based on whether the final number is above or below 0. Now consider a simple example in 2 dimensions. Suppose we have 6 data points. The first 3 points are labelled positive, and the last 3 are labelled negative. We can plot these points on a plane. The learning algorithm's job is to find a line that separates the positive points from the negative ones. Instead of searching over all possible models, we compare 2 candidate models to understand how evaluation works. The first model applies a linear rule to the inputs, while the second model uses a different linear rule. We run both models on the training data and count how many mistakes each one makes. For the first model, all 6 points are correctly classified, so the training loss is 0. For the second model, 1 point is misclassified, so its loss is 1 out of 6. Since the first model makes fewer mistakes, the learning algorithm prefers it. Geometrically, classification models divide the input space into regions. One region is labelled positive and the other negative. A good model places all positive examples in the positive region and all negative examples in the negative region. Now consider another example involving house pricing. We might build different models that combine features like number of rooms and distance to a metro station using different weights. We evaluate each model by computing predictions on the training data and measuring how far those predictions are from the true labels. The model with smaller overall error is preferred. However, an important idea arises here. A model that performs perfectly on training data is not necessarily the best model in general. For example, it is possible to construct a model that memorizes specific training points and predicts correctly only on those points, while performing poorly on new unseen data. This leads to a key principle in machine learning. We must evaluate models on data they have never seen before. So we split data into 3 parts. First is the training data, which is used to learn the model parameters. Second is the test data, which is used only to evaluate how well the final model performs on new unseen examples. Third is validation data, which is used to choose between different types of models or different model structures. For example, one might compare linear models with different feature combinations and decide which model family is best using validation data. In summary, supervised learning involves learning a function from input to outputs using labeled data. Classification is the case where outputs are discrete labels. We train models by minimizing classification errors, but we evaluate performance using unseen test data to ensure the model generalizes beyond the training set. In the next lecture, we will move on to unsupervised learning.
Hello everyone, and welcome to another lecture on machine learning foundations. In the previous lectures, we introduced supervised learning and studied the 2 main types of supervised learning problems, which are regression and classification. In this lecture, we begin unsupervised learning and focus on two main tasks: dimensionality reduction and density estimation. Unlike supervised learning, where we have clear input-output pairs and a clear goal, unsupervised learning is much less clearly defined. It is often used as a preprocessing step rather than a final goal. At a high level, unsupervised learning is about understanding data. In this context, data simply means a collection of vectors. Unlike supervised learning, where each data point has an input and a label, here we only have inputs. So we just have vectors, without any associated outputs. The goal of unsupervised learning is to build models that can compress data, explain data, or group data. In other words, the goal is to understand structure in the data. We will make this concrete using two examples: dimensionality reduction and density estimation. To see why unsupervised learning is useful, consider a real-world scenario. Imagine you're a marketing manager at Coca-Cola, and your job is to summarize tweets about the brand. Suppose there are 1 million or even 10 million tweets in a week. You cannot read all of them or report them individually. Instead, a useful strategy would be to group these tweets into a small number of categories, say 10 groups. For example, one group might be people posting selfies with Coke. Another group might be business collaborations. Another might be promotional campaigns. Once these groups are formed, a human can interpret them and assign meaning, and then report a summary to management. The key idea is that the algorithm only performs the grouping. It does not understand the meaning. The human assigns meaning afterward. This is why unsupervised learning is not usually an end goal by itself. It produces structure, but humans interpret that structure. Now we move to a concrete and supervised learning task called dimensionality reduction. The goal of dimensionality reduction is compression and simplification of data. For example, imagine a genetics company that collects gene expression data. Suppose there are 1 million people, and each person has 1 million gene measurements. This creates a massive dataset with 1 trillion numbers. Storing or transmitting this directly is impractical. So the goal is to compress this data into a smaller representation that still preserves important information. Formally, we start with data points that are vectors in a high-dimensional space. Instead of learning a single model like in supervised learning, we learn two functions, an encoder and a decoder. The encoder takes a high-dimensional vector and converts it into a lower-dimensional vector. The decoder takes this compressed representation and tries to reconstruct the original vector. So the encoder compresses the data, and the decoder decompresses it. The goal is that if you encode a data point and then decode it, you should get back something very close to the original input. We measure how good this is by computing the difference between the original vector and the reconstructed vector, and squaring its length. We then average this over all data points. Now let us look at a simple example. Suppose the original data is two-dimensional, and we want to compress it into one dimension. We have 4 data points, one point near 1,0.8, another near 2,2.2, another near 3,3.2, and another near 4,3.8. Now we define a first encoder-decoder pair. The encoder takes a point and computes the difference between the first coordinate and the second coordinate. The decoder takes the single number and maps it back into a two-dimensional vector, where both coordinates are equal to that number. If we apply this system, we see that very different original points all get mapped to very similar reconstructed points. For example, both 1,0.8 and 4,3.8 end up producing almost the same reconstructed output. This means the encoder is losing too much information. It is compressing the data, but not in a useful way. Now consider a second encoder-decoder pair. This time, the encoder takes the average of the two coordinates. The decoder again reconstructs a two-dimensional vector, where both coordinates equal this average value. When we apply this method, the reconstructed points are much closer to the original data points. Each reconstructed point is now a reasonable approximation of the original input. So this second method is clearly better because it preserves the structure of the data much more faithfully. If we visualize this, we see that the first method collapses many different points into the same representation, while the second method preserves relative differences between points. In general, real dimensionality reduction algorithms do not choose between just two fixed encoders. They search over a large space of possible functions to find the best compression and reconstruction pair. With this, we complete the introduction to dimensionality reduction in unsupervised learning. Hello everyone, and welcome to another lecture on machine learning foundations. In the previous lectures, we introduced the supervised learning setting and studied its two main types of tasks, regression and classification. In this lecture, we begin unsupervised learning, along with its two main tasks, dimensionality reduction and density estimation. Unlike supervised learning, which has clear inputs and outputs and well-defined goals, unsupervised learning is much less rigid. It is often used as a preprocessing step rather than a final goal in itself. Unsupervised learning is broadly about understanding data. In our setting, data simply means a collection of vectors. Unlike supervised learning, where each example has an input vector and a label, here we only have input vectors. There are no labels. The goal of unsupervised learning is to build models that can compress data, explain structure in data, or group similar data together. We will understand this through two main examples, dimensionality reduction and density estimation. Dimensionality reduction. Dimensionality reduction is about compression and simplification. For example, imagine a genetic dataset where we store gene expression levels for 1 million people, and each person has 1 million gene measurements. This creates a matrix with 1 trillion values. Storing or transmitting this directly is impractical. So we want to compress this high-dimensional data into a low-dimensional representation while preserving as much information as possible. Formally, we start with data points that are d-dimensional vectors. The goal of dimensionality reduction is to learn two functions. First, an encoder function, which takes a d-dimensional vector and maps it into a smaller dimensional vector. Second, a decoder function, which takes that smaller vector and reconstructs an approximation of the original d-dimensional vector. So the encoder compresses the data, and the decoder tries to reconstruct it. The goal is that if we encode a data point and then decode it, we should recover something very close to the original input. In other words, decoding after encoding should approximately give back the original data point. To measure how good this is, we compute the difference between the original vector and the reconstructed vector, square its length, and average this over all data points. The goal is to minimize this reconstruction error. Now consider a simple example. We have two-dimensional data, and we want to compress it into one dimension. We define an encoder function that maps a two-dimensional vector into a single number, and a decoder that maps that number back into a two-dimensional vector. One example encoder is the difference between the first and second coordinate. The decoder then simply repeats this value in both coordinates. If we apply this to sample data points, we find that different original points can collapse into the same reconstructed output. This means information is lost, and the reconstruction is poor. Now consider a better encoder. Instead of taking the difference, we take the average of the two coordinates. The decoder again repeats this average into both coordinates. This reconstruction is much closer to the original points. So this encoder-decoder pair preserves structure better and gives lower reconstruction error. Density estimation. Now we move to density estimation. Density estimation is about building a probabilistic model of data. The output of such a model is a function that assigns a probability to every possible input. For example, suppose we want to model tweets from a user. Each tweet is a sequence of characters, and we want to assign a probability to every possible tweet. A good model assigns high probability to tweets that look realistic, and low probability to unrealistic ones. The key constraint is that all probabilities across all possible inputs must sum to 1. So we cannot assign high probability to everything. The total probability mass must equal 1. To train such a model, we use data and maximize likelihood. More precisely, we minimize the negative log likelihood. For each data point, we compute the negative logarithm of the probability assigned to it, and then average this over all data points. A good model assigns high probability to real data points, which makes the loss small. Now consider a simple, one-dimensional example. We have 4 data points on a number line. We compare 3 probability models. The first model assigns equal probability across a wide interval. The second model assigns equal probability over a smaller interval that better matches the data. The third model assigns probability outside the data range in a way that excludes some data points. When we compute negative log likelihood, the second model performs best because it concentrates probability where the data actually lies. The third model performs worst because it assigns 0 probability to some observed points, which leads to infinite loss. Another example uses more complex models like Gaussian mixtures. Here, data appears to form clusters. One model places Gaussian centers near the actual clusters in the data. Another model places centers far away from the data structure. The first model is clearly better because it matches the structure of the data and gives lower negative log likelihood. Summary unsupervised learning has no labels. Its goal is to understand structure in data. Dimensionality reduction compresses data using encoder and decoder functions. Density estimation builds probabilistic models that assign likelihoods to data. Both are evaluated using reconstruction error or negative log likelihood. This concludes the introduction to unsupervised learning. Hello everyone, and welcome to another tutorial on Introduction to Machine Learning and Data Analysis. Let's get started. We begin with a discussion about beneficial and harmful placements of data and models. Think about situations where something is not clearly giving us useful information or structure. We often work with large datasets and need to make sense of them. For example, we may have dual SIM data migration systems or general data processing tasks where everything is about data and labels. We may have around 7,000 data points with corresponding labels, and we want to understand relationships between them. These labels may represent different categories or outcomes. We often try to understand relationships between features in the data, such as relationships between variables like date of birth and some outcome value. The goal is to learn patterns from data so that we can make predictions. For example, we may try to understand relationships between different geographic locations or city-level data. In machine learning, we typically subscribe to the idea that we should learn relationships between data points using a model. We are often given datasets where both inputs and labels are available, and we try to build a model that captures the relationship. We may want to understand ordering, such as ascending or descending order in data values. We may also deal with classification problems, where we try to assign labels based on input features. In classification, we build a model that maps input data to discrete labels. For example, a linear model or a non-linear model can be used depending on the complexity of the data. We also evaluate models based on how well they perform on classification tasks. In many cases, data alone is not enough. We need meaningful relationships between points, not just raw values. We try to understand sequences and structures in data rather than treating data as isolated points. We may also work with real-world datasets collected from different sources, such as sensors, communication systems, or service centers. These datasets may be large and complex and require careful modeling. We often study how to construct models that can generalize well and avoid overfitting to specific datasets. The main idea is that a model should not just memorize data, but understand the underlying structure. We aim to build models that can work well on unseen data, not just training data. This leads us to the core idea of machine learning, learning patterns from data to make future predictions. We continue exploring different types of models, including classification models and regression models. These models help us understand relationships between variables and make predictions based on input data. Ultimately, machine learning is about extracting meaningful structure from data and using it to make informed decisions. This lecture is about how machine learning uses a real dataset for classification, specifically breast cancer detection. We start with the dataset structure. Each row in the dataset represents one patient. Each column represents a measurement or feature of that patient, such as tumor radius, texture, perimeter, and so on. There are about 569 patients in total, and for each patient, there are about 30 measured features. So instead of thinking in terms of a table, we think like this: each patient is a data point, and each data point is a list of 30 numbers. We call this list a feature vector. So, the ITH patient corresponds to the ITH feature vector, and the JTH feature of the ITH patient means the value of the JTH measurement for that specific patient. For example, if we say patient number 128 and feature number 28, we mean the 28th measurement of the 128th patient. Now we also have labels. Each patient has a diagnosis, either benign, meaning non-cancerous, or malignant, meaning cancerous. We convert this into numbers so the model can understand it. So benign becomes 0, and malignant becomes 1. So each patient has a feature vector as input and a label as output. Now we build a machine learning model. The model takes a patient's feature vector and outputs a prediction, either 0 or 1. For example, if the model predicts 0 for a patient, it means it predicts benign. But if the true label is 1, meaning malignant, then the prediction is wrong. In that case, we assign a loss of 1. If the prediction matches the true label, the loss is 0. So the loss is simply 0 for correct prediction, 1 for incorrect prediction. Now we try to understand the data visually. If we only take 2 features, for example tumor radius and texture, we can plot the data in 2 dimensions. Each patient becomes a point on a graph. We can then try to separate cancerous and non-cancerous cases using a boundary. But the problem is, the data is not cleanly separable with a straight line. So a simple linear model does not work well. A linear model tries to draw a straight boundary using weights assigned to each feature. Different choices of weights give different straight lines. But most straight lines will not separate the data well. Even in 3 dimensions, where we add a third feature, we get a flat plane instead of a line. But the same problem remains: the data still overlaps. We can extend this idea to all 30 features. Instead of a line or plane, we now have a decision boundary in third-dimensional space. This is impossible to visualize, but mathematically, it works the same way. The model learns a set of weights for all features. These weights define the decision boundary. Now we train the model. We do not manually choose the best boundary. Instead, we use an optimization method that automatically finds the best weights that reduce error. Finally, we split the dataset into 3 parts. 1 part for training the model, 1 part for validating and tuning the model, and 1 part for testing the final performance. The key takeaway is this: each patient is represented as a high-dimensional vector. The model learns a function that maps this vector to a diagnosis. Even though simple linear models are intuitive, real data is often more complex, so we rely on learning algorithms to find good boundaries automatically. In the previous video, we looked at a breast cancer classification dataset. Each sample in that dataset has many features, about 30 different measurements per patient, and the goal is to classify whether a tumor is malignant, meaning cancerous, or benign, meaning non-cancerous. Now the question that naturally comes up is, do we really need all 30 features, or can we represent the same information using fewer numbers, like just 3 values? Even though modern computers can easily handle 30 features, and even much more, the real motivation is what happens when scale increases. If instead of 30 features we had 1 million features, that becomes heavy in terms of memory, storage, and computation. So the idea is to reduce the number of features while keeping most of the useful information. This is called dimensionality reduction. We're now in an unsupervised learning setting, meaning we only have data without labels during this step. Even though the original dataset is for classification, we use it in a pipeline like this. First, we take each sample, which originally has 30 features, and we compress it into a smaller representation, say 3 numbers. So each data point, originally a vector of size 30 by 1, is transformed into a vector of size 3 by 1. We do this for every sample in the dataset. After this compression step, we can take these 3-number representations and then use a supervised learning model, like a classifier, to predict whether the tumor is malignant or benign. This has 2 main advantages. First, it reduces memory usage because we store fewer numbers per sample. Second, it reduces computational cost. For example, if we originally had 1 million features, a simple linear model would need 1 million weights. But if we reduce it to 1,000 features, we only need 1,000 weights, which is much more efficient. Now the key question becomes, how do we actually convert 30 numbers into 3 numbers? We can think of this as a function that takes a vector of size 30 by 1 and outputs a vector of size 3 by 1. One simple example of such a function is a matrix multiplication. We define a matrix that has 30 rows and 3 columns. When we multiply this matrix with the original data vector, we get a compressed representation of size 3 by 1. So each sample is transformed using this matrix, and the matrix contains parameters that are learned using some learning algorithm. In total, this matrix has 90 parameters. Once we have this compressed form, we can also think about reconstruction. If we want to send data over a network, instead of sending all 30 numbers, we can send only 3 numbers. At the receiver side, we can try to reconstruct an approximation of the original 30 numbers using another transformation, often another matrix. Under certain conditions, this reconstruction can be done using the transpose of the original matrix. So the compressed vector is 3 by 1, and the reconstructed vector is 30 by 1. The reconstructed version is not necessarily identical to the original, but it should be as close as possible. This idea is used in real applications like image compression. Instead of sending a very large number of values, we send a smaller compressed representation and then reconstruct it later. Next, we move to another unsupervised learning idea called density estimation. In density estimation, we assume that all data points come from some underlying probability distribution. For example, in the breast cancer dataset, we have about 569 samples, each with 30 features. We can imagine that these samples are generated from some unknown distribution. If we can estimate the parameters of this distribution, such as the mean and variance, then we can generate new synthetic samples by sampling from the same distribution. For visualization, if we only take 2 features, like radius mean and texture mean, we can plot them on a 2-dimensional plane. The distribution of each feature could be thought of as a smooth curve, and together they form a joint distribution. Once we estimate this distribution from the data, we can generate new data points that look similar to the original dataset. This idea scales to very high dimensions, like all 30 features together. In practice, the goal is to learn the structure of the data well enough that we can generate new realistic samples. A well-known example of this idea is face generation systems. Models trained on millions of face images can learn the underlying distribution of human faces and then generate new, realistic-looking faces by sampling from the learned distribution. So overall, dimensionality reduction helps us compress data into fewer features, and density estimation helps us model the distribution of data and generate new samples from it.